You've heard from a couple of consultants. Now you're going to hear from someone from the company of whom it used to be said, if it's good for General Motors, it's good for America. And we want to hope that that's still true.
I hope so.
So I present to you, and you just told me how to pronounce it. And
Tilove.
Thank you. Instantly forgot. Bob Tilove of General Motors R&D. Please help me welcome Bob.
Thank you. It's a pleasure to speak with you this afternoon. I hope what I say is interesting enough to hold your attention for just a few more little bit. I want to talk about challenges of realistically simulating manufacturing, and there are a great number of such challenges, but I'm going to focus on a particular area that's been occupying some of my time and energy lately. Today's virtual manufacturing engineering software doesn't solve all of our problems. There's some great stuff out there. But I want to give a particular example of a kind of problem where I think there certainly are some very interesting R&D challenges to be working on, and that also might stimulate a little bit of rethinking about our CAD, CAM, PLM systems. So I'd like to provide an example and explore a little bit this vision. And I'm very interested in getting some feedback from you all about how crazy you think I am. So I want to talk specifically about human work environments. A lot of times when you say virtual factory or virtual manufacturing, people have this image of nice graphics with lots of robots and conveyors and automation. Sometimes you see cartoons of people walking around in them. But I really want to focus here on the human work environment. I'll give some examples and then go through what I see as the vision and challenges and summarize. So these virtual work environments are where people are performing work. And so here's an example from automotive. But one of the reasons I want to come and discuss this here today is because it's not an automotive problem. These same issues appear in defense and aerospace and construction, in consumer electronics, and so forth. So I'm really talking about wherever we have people doing work. They're pervasive. Ergonomics and safety are overarching concerns in the design and validation of these environments. And manufacturing ergonomics, quality, throughput, and issues, and this is based on my experience in looking at GM data regarding issues that are discovered, relate primarily to things having to do with human posture, motion, reach, access, vision, with the exertion of force, both static and dynamic. And the forces that are involved here relate not only to rigid body dynamics, picking up a load, but also to the assembly process itself, which involves deformation of non-rigid objects. So these are sort of the themes around some of the R&D challenges that I'll be discussing here in the talk. So I have a funny name for these things, and the reason it's a funny name is because, to start with, there are things called simulated work environments. We use this term in GM, and I am pretty sure that it's used in other industries as well. And the idea of a simulated work environment is we bring real operators into a laboratory where there's mock-ups of the parts and the tools and the conveyance and so forth. And we use this environment to train the operators on the task and to allow the operators to collaborate, to improve the layout of the facility, improve their own productivity and comfort. But it's real people working with physical prototypes, and we call that simulated work environment. So my name for these things is virtual simulated work environments, and that's why it sounds like there's too many words, virtual and simulated. I basically would like to be able to do in the computer everything that I do today in these simulated work environments. So that is design, validate, and operate them. I'm thinking about assembly, repair, maintenance, tasks, disassembly tasks, And the key things here is the human operator manipulating both flexible and rigid parts and tools requiring the exertion of force. So, you know, why are we interested in these things? And I want to emphasize that, you know, we want to use our virtual methods to validate and optimize our designs and our process plans to eliminate prototype parts and costs, to identify issues earlier, to reduce our costs and time, improve our safety. It's not about pretty pictures. Sometimes pretty pictures help to do this, but the pretty pictures rely on the human to interpret the pretty picture and to identify the problem. It's much better if the computer can do that for us. And I'll maintain that our current virtual engineering tools are inadequate for these types of problems, and we'll walk through the details here in a minute. So as a result, yeah, I probably should have brought a chart. Hasn't been technically cleared for me to show, so I won't. But if you would imagine our vehicle development process rolling out over time and lay out underneath it when we discover issues, ergonomics type issues, issues that are associated with human operators and these sorts of things, what you find is during the phase of the process where we're using mostly our computer simulation tools, our PLM and CAD-CAM and Teamcenter and all that, we're finding very, very few problems. It's when we start to build the hardware and get the physical prototypes that we discover a lot of the issues. And that's too late. The second motivation is, of course, similar, you know, the current simulated work environment, that these will enable us to use these computer methods, simulation methods, earlier in the process to train operators and to you know, optimize our workplaces. I'm going to be talking mainly about the first kind of motivation, finding and fixing problems, although this is very interesting by itself to consider how well these virtual techniques can be used for training as opposed to other methods that we use today. Okay, so we'll get into the sort of more technical part of the talk. And by the way, nothing is too terribly technical, but maybe there'll be an equation or something. So I'm laying this out in terms of what I see as generations of capability, how this might roll out in time. And at the end of the day, what I'm interested, as I said, virtual simulated work environment, completely validating the task in the computer. And I think about this in terms of two swim lanes. The top has to do with the modeling of the parts and the environment, the interaction between the parts and the environment. So we'll talk about flexible parts modeling and assembly force prediction. The bottom part has to do with the human models, the digital human models, how realistic they are, how easy they are, how automated they are, how well they comprehend accurately the force exertion requirements. And then those things have to kind of come together at the end of the day to provide this virtual simulated work environment. So the way I've structured the talk is I want to kind of walk through it in this timed sequence. So I'll start by talking about flexible parts and realistic human models, and then I'll move, you know, into the later phases. Okay, so first research challenge is modeling flexible parts. So solid modeling, for those of us who were around back in the day when, we know that it began as a manufacturing initiative. I mean, it started because there was an interest in simulating machining and in being able to automatically program machine tools to produce things. We have made tremendous progress since those early days in terms of the amount of data or the complexity of the model, the assembly that we can, you know, put into the computer. But the domain is still rigid solid objects and mechanisms with rigid links. We have good mathematical characterization of what that means. So been great progress in computational complexity, but the domain has really not changed. And of course, if you look at our products or aerospace products or consumer electronics products, capital goods products. There's a lot of flexible parts in there, and they're important to model. So I'll start a couple of videos here and let them play while I talk. And these are demonstrating some of the emerging capabilities that are available today as a result of research that's been conducted over the past, say, 5 or so years. So relatively new stuff. And I want to make a couple of points. First of all, these are real time. If you look at the robot dress example here in a minute, you'll see the user is able to pick up a clip location and move it around, and that is happening in real time. And if you continue to look, you'll see it can deal with cables with branches, and if you look very carefully, you'll see, oh, it didn't handle the collision with the rigid object very well. This is a few years old, and that now has been fixed. The other illustration here is more of an assembly operation involving, hooking up the cables to a radio for an installation in a vehicle. And the first time I showed this to a manufacturing executive at General Motors, she said, wow, this is really great. Now, of course, you can tell me if the operator can reach in there and whether they can, actually get the connector to connect. And I had to say, no, not yet. I'm working on that, so that will motivate some of the rest of the talk that comes later. But these are all very simple cross-sections. They assume linear elastic material properties. They're quasi-static. They're interactive, but they're quasi-static. But they're physics-based and they're verifiable. That is to say, I can measure in a laboratory and scan these parts. And if the parts are linear elastic materials, these calculations are quite accurate. So, of course, the research challenge is I need to extend this. I need to extend this to something like the wiring harness, the real wiring harness, which, as you can see, is sort of a disaster, and other kinds of materials that are more complex in terms of their geometry, but also much more complex in terms of their material properties. And that really is going to be the challenge, I think, is dealing with these composite materials. But I'd like to be able to do anything with them that I can do with solids, which includes things like path planning. Okay? So that's research challenge number one. By the way, I'm willing to entertain questions as I go through here as well, if you have any. So next I want to hop down to talk about the digital human aspect. I'll start one of these as an animation. I'll start this guy going while I'm talking. So we've had these mannequins around, these computer mannequins around for quite some time. The issue with them is that it's very difficult to posture these mannequins realistically. I mean, a simulation engineer, usually there's like a posture library that's available, or more often the simulation engineer will decide, well, I'm going to let Jack or Jill stand here and ask, to reach there. And, well, it didn't work because the head bumped into something, so I will manipulate the pelvis, or I will manipulate the elbow or the shoulders or the fingers or the hands or the wrist, joint by joint by joint by joint, in order to get something that looks somewhat reasonable, or at least convinces me that I can reach or access the work. It's so difficult to do this that a lot of sophisticated users resort to motion capture devices, okay? Where they'll suit somebody up in a motion capture suit, they'll put them in a laboratory environment with some mix of physical mock-ups and virtual images, and they'll have the human, do the reach. They'll record the posture of the human, and then they'll take that data and they'll feed it back into the digital mannequin to get the joints of the digital mannequin to look at the ergonomics issues. This, to me, is not the way we want to go. I don't want to have to wait for physical parts. I would like the mannequin to be smart enough to be able to posture itself realistically in these cluttered environments. The other point I wanted to make, the dynamic capabilities of these models are also pretty limited. So an animation like the one that's shown here you can see that, first of all, there's all these weird, there's a weird postures there because the simulation engineer said, oh, I have to do something because otherwise she's going to bump into the table. But they're done by keyframing. So the simulation engineer defines the posture of the pose at certain key places, and if all of a sudden you blink and everything has changed, that's because that's the amount of effort that the simulation engineer put into it. It's an animation, so what I would like to be able to do is, I have a work instruction sheet, something similar to the job element sheet that I give a real operator that's in my process planning system. I have all the 3D geometry. I'd like to hand those to the digital mannequin and have the mannequin automatically position itself. And when I reviewed this with Brad, he said, oh, I get it. It's sort of like before the human was teaching the digital, the real human was teaching the digital human. Now the digital human is going to be teaching the operator. So that's where I'd like to be able to get to. And we're pretty far away from being able to do that today. There's a couple of approaches. It is an active area of research. In some places are using semi-empirical approaches where they will suit up real people in motion capture devices. They do that in order to collect data on how real humans move and what strategies they employ. And they try to convert that, those empirical measurements into algorithms that they can use at runtime. There's other methods that are based more on optimization that are more like robotic path planning, if you will, where they try to calculate joint angles that minimize or optimize a whole bunch of criteria. And I think the cards are still out about which one of these methods are going to win out. I think probably maybe there will be some combination of both. Certainly we need to have the empirical data in order to validate that the optimization or the mathematical approach is valid, if nothing else. Okay, so now I'm going to move into the second generation here and talk about assembly force prediction and force-aware digital humans. So the huge application of solid modeling, of course, has been in interference checking, collision checking, proximity checking, packaging, motion planning, all the rest of that sort of stuff. And it's good stuff. As soon as you admit that there are flexible parts in the world, the question is no longer do they interfere, but how do they deform when they come into contact with other flexible or rigid parts, and what forces are required to deform and manipulate and assemble them. So this is moving from solid modeling to a term I borrowed from Vadim. I call it physical modeling, and I think it's really a huge R&D challenge. So here is a sort of an example from my world, what's going on here. We have a lot of these clips, we use for fastening parts. And when we get the clip, the supplier of the clip gives us data on the insertion force and the retention force for that clip. But the data that we get from the supplier is based on a single clip being inserted with a straight load path into a rigid substrate with a very clean hole. And in the real world, none of those things really are true, okay? There are usually multiple clips on a trim part, and as a result of manufacturing variation or whatever, I don't have the luxury of having straight insertions except for maybe the first time. Also, I'm pushing not into a rigid substrate, I'm pushing into a compliant substrate, and that bending has an impact. Sometimes I'm compressing soft materials in between so that the work the operator does is partly the work that's associated, with the pure insertion of the fastener, but it's also the work that's required to overcome all of these other factors, which can very significantly outweigh, the data that we got for insertion force. Here's another example on hoses, and I won't go into a lot of detail here, except you know, you might think that this business of being able to predict the insertion force for a rubber hose on a connector might be not so hard. What makes it hard is that the hose is not a pure rubber material. It's a composite material, and we don't really have good material models for those composites. So let me just start a couple of animations here that illustrate some of the work in progress here. The one on the left is showing, again, it's a single clip, but now going into a compliant substrate. And the boundary here is fixed. So you can imagine that boundary as having something to do, for example, with the nearest clip that might be fastening or constraining the boundary of the part. And you see what happens, of course, is as you push that clip in, the substrate deforms. And if the clip is attached, of course, to a trim part. And if the clip is not completely inserted by the time the trim part comes down into contact with this boundary condition, then I actually have to start to deform the trim part in order to push it in far enough to complete the insertion, and that's what gives rise to these excessive forces. So this is the first step at being able to analyze that. And then this is showing an example of an insertion operation, a hose insertion operation involving a combination of pure pushing and pure twisting. So we can deal with these with sort of traditional, more or less traditional CAE modeling techniques, although the materials are a challenge here. And there's many, many different types of these kinds of problems. I have a list this long, you know, that the industrial engineers tell me if I can find these problems, then, you know, they'll be happy. And these are only just two of them. So I think the key here is this, you know, because I want to be able to do this in a simulation, as I'll show you here on the next slide, a few slides from now. I want to really be able to do these very, very quickly. So in my mind, the question is there a way to approximate this without having to solve differential equations and go back to a CAE finite element method, some kind of a lump parameter model? I don't know the answer to that yet, but I think that that's the kind of thing that we need to be looking at. Okay, and then the corresponding issue with respect to digital humans is really, you know, exemplified by this picture. Today, DHMs behave like Superman. They walk through anything, which is a little bit funny. They can see through anything. But if you ask Jack or Jill to pick up a box using a posture in the posture library, they will pick up that box, and it doesn't matter how heavy the box is. The motion or the posture will always be the same. And of course, real people adapt and select their postures in relation to the forces that they need to exert in the environment. They do that in very, very clever ways. They employ some very clever bracing strategies to assist in exerting those forces. So, you know, the first part of the DHM challenge is just get them to be able to posture themselves realistically in cluttered environments without individual manipulating of the joints. This is have them also adjust their postures and motion in relation to the forces that they need to exert when they perform the tasks. Okay, and so now we come to the last bit, which I think might be most interesting to the software vendors, PLM type vendors in the room, is how does this all come together at the end of the day in what I call the, you know, virtual simulated work environment. So I said before, the idea is I'm going to hand, whoops, a little touchy. I'm going to hand the job element sheet, or the equivalent of the job element sheet, or the process plan. Oh, this must be on a rehearsed timing. I hate that. To the digital human, who is going to execute the work according to the work instruction, but it knows about the environment, and also I now have this real-time physical modeling system. It's not just a solid modeling system. I understand the forces and deformations that occur during the assembly task, so I calculate those in real time, and that affects the posture and motion of the human, and it all operates in a tight simulation loop, is the vision. But of course, these different capabilities cross the traditional silos in our CAD, CAM, CAE, PLM type systems, okay? one piece of information is in the process planner, another is in the process simulate tool, another is in the CAE tool, and we have a hard enough time moving information from one of these silos to another in batch mode. I'm talking about doing this in real time. I mean, I want to hook the input of one to the output of one to the input of the other, and the output of one to the input of the other, and do this in real time. So how is that all going to work? And what kind of information model is going to allow those to communicate in real time? So this brings us to near the end of my talk about rethinking virtual manufacturing. So today, if I'm going to simulate, say, a work cell in the current tools, I simulate that whole work cell. If there's 3 robots, there's 3 robots in my simulation model. And if the input to that work cell is a subassembly, I get that subassembly from the design data as designed. So I call that fragmented simulation as designed. Fragmented because I do this just for a work cell, okay, and because it takes so long and it's so time consuming to build these simulations, I don't simulate all work cells this way. I simulate only the ones where I think that I might have an issue or where I found an issue, and I do the simulation in order to remediate it. So that's why it's fragmented, and as designed is what I mean here, that the data is the perfect design. What I'm thinking in terms of the future is something that you might call seamless simulation as manufactured. So if the input to something is a subassembly, I want to get that input as the simulated result, the as manufactured result of the step before in the process, and hook input to output to input to output. In my simulations, the same way I hook input to output to input to output in my factories, and have those individual modules communicate with each other using the plant floor network. Okay? So I have parts that flow through what now is a distributed emulation of the factory, and I'm controlling that simulation with my plant floor controls, initially in soft PLCs, and the parts could either be as designed parts, or they could be actually as manufactured, the predicted result of a simulation of the manufacture of those parts, or scan data, or something like that. So the whole idea is to move from this monolithic simulation of a work cell to actually something that looks like a virtual factory. And it becomes distributed simulation using a plant floor network. And the whole discussion about cloud computing and is I think relevant here to actually the feasibility of being able to do something like this. And of course, if I set it up like this, then there's really no difference in this model between the real and the simulation, so that I can selectively replace elements of this with the virtual model of what that device does, or the real device. I just unplug the simulated process and I plug in the real process. And I can do this in any combination of real and virtual resources. And of course, I'm sweeping a whole lot of details under the rug here, having to do with how you synchronize this and how you hand a virtual part to a real robot, things like that. So there are details here. But I think this is the general direction that we want to be thinking. And you may have heard about or read about things called virtual commissioning. That's clearly a first step in this, but the virtual commissioning side is focusing primarily only on the controls. And I see this as a whole different way to architect the virtual factory. So where this kind of goes to is this idea that the next generation, here's our production monitor or our SCADA or however you want to say the operator consoles where they're looking at everything that's going on in the plant. And what I'm thinking is that in the future, behind the curtain, the people who are looking at those displays do not know whether they're looking at a real plant floor or a virtual emulation of that plant floor or some combination of the two things. And that becomes very, very powerful for planning and validating changes to an existing plant. and applying these tools in the continuous improvement and operations of the plant. So that's where I think this stuff should be kind of heading. So just quickly, with a summary, if that vision makes any sense, then there's a couple of things that we need to do. The first is we need to fill gaps in our simulation tool set because we don't have the capability today to simulate some things that we would have to be able to simulate if I were going to run a virtual factory at that level of fidelity. And I gave two examples, but there are others. One is flexible parts. We don't have the capability today. The other is assembly force prediction. We don't have the capability today. But even if we have the capability, we have to dramatically reduce the cost and time that's associated with creating these simulation models. You know, they have to be much more intelligent and automated. And I gave an example of that in the digital human model. And then the third thing that we have to do is basically rewire the virtual factory, which is an architecture. And so I see here some potentially disruptive technologies. The first, from solid modeling to physical modeling. And the second, from this idea of fragmented simulation as designed to seamless simulation as manufactured, which gets us, you might call that distributed hybrid emulation with plant floor controls. And I think we'll probably, at the end of the day, look much more like multiplayer virtual worlds than like today's virtual factories. And when you take those two things together, what it's saying to me is rethink our PLM, where today an assembly is a configuration of design data. Somebody this morning referred to it as a bill of parts. Rethink PLM, that assembly, rather than being as a configuration of design data, to assembly as the process for putting this stuff together. And so that's the challenges that I see. Also, I think these they represent a significant generic manufacturing R&D challenges with applications in a lot of places which would benefit from more collaboration to leverage resources, accelerate R&D, maybe get some government funding. So if any of you have ideas along those lines, I'd be happy to speak with you. I'm already collaborating with some of your companies in all of this work, because this is not, you know, this is not GM specific. This is for the good of the world. So, thank you very much.
Any questions for Bob?
Yeah, the risk is sounding a little bit crazy here. I'm just going to throw this out there. At the same time that this is all evolving, you've also got the robotics side that's evolving, the vision systems side that's evolving. At some point in time, these things might merge.
Sure.
You don't need even
Sure. But the problem doesn't go away. Okay, so I have a counterpart, you know, in my lab who is the robotics guy. You know, you've seen the Robonaut pictures and stuff like that. I don't know if you've seen those. Anyways, so instead of the human, I have the robot who has I have the same issues with respect to planning, robot motions, and validating my work environment for the robot. But yeah, I also don't think that humans are going to be out of the equation, you know, anytime soon. And certainly in a lot of the other industries that I talked about, I don't really see that happening. You know, if you look at aerospace, for example, I mean, a lot of that is, you know, manual assembly, and I think it's probably going to stay manual assembly. So if that was your point, why worry about the human so much?
I see how you need all this math and science to create the models, and the logic and the algorithms to get these virtual people to calculate it all automatically. If you've gotten to that extent, you're halfway there. And actually, you have this automated in the first place.
Right. Right. So
there is no limit.
Well, yeah. Well, I mean, I still hand the robot the equivalent of a job element sheet. So they still need to be able to plan. So I understand the point, but what I'm trying to say is, you know, everything that I talked about, the robot interacting with the environment, being able to factor that interaction into the simulation, and then be able to insert into the simulation changes, things that change, and have the robot, you know, do the right thing. It's fairly very similar. It means it takes the emphasis away from the human and onto the robot, but the issues are really very similar. You know what I'm saying? How, if you were to imagine a dexterous robot with vision systems and all the rest of that stuff, how do you program their task? My claim is today you end up doing it very similar to the way I program my digital human. Okay? So what I'm calling for, and that slide that I showed where I said one of the approaches to solving this is very much like a robotics motion planning approach. It would be a very, very similar approach, just a different mechanism.
At the risk of an inside joke, I think maybe it's more like you're being solve this problem and target 100 of critical automotive and roll update. But the joke was sometimes more to solve something which is very exotic, probably to solve using inexpensive stuff like that. But I don't think this is going to be that easy to solve. It seems like the core problem we have is one of the representation of your basic objects. And I'm talking computer objects that represent real world objects. And the difficulty in most gadgets is to solve modern systems if they don't handle abstraction of objects very well. That is, say something as simple as an automotive pose, they might be able to represent it and solve a model, but that's sufficient for one application, but it's not sufficient for other applications. There may be multiple incarnations of that, we call them avatars of your life. But I think the challenge will come down to a very core issue of how the objects are defined in the system. And current software simply doesn't handle object abstraction very well.
Right, that's what I was trying to get at when I talked about physical modeling. So it's more than just the abstracting the part as a rigid solid. It's understanding the physics of that part of the
Also be flexible enough to change that model as you need to do abstraction. As you gain more information about material, and materials change, or if you consider the human to be a material system, which it really is, it's a very complex part. The model has to be expandable or growable.
There's a huge amount of research being done on that exact subject right now in the multi-scale model, where you go from the molecular to the macro and from all the way up. Could I just inject it for a second? I mean, one of the things that I think is worth pointing out is that in the field of manufacturing, it's an inconvenient truth that the things that are worth modeling in manufacturing assembly are unfortunately non-linear. Otherwise, they're not worth modeling. So there are some state-of-the-art work being done right now in which, for example, the hoses and the wires are included in non-linear formulation. So, and the second thing that I'd like to point out, maybe to fuel some discussion, is that I absolutely agree with your vision, and it's something that I've been working on for a while. But the frustration of connecting the traditional industries where simulation has been taking place, like automotive and aerospace, with some of the emerging industries where they are significantly ahead. So if you take mundane products like detergent, today companies are modeling the interaction of the human hand and the grip with that detergent bottle, including the nonlinearity of the fluid, the container, and the human tissue. Take medical devices, the insertion of stents in the femoral artery. They're modeling the whole insertion process, the deployment process, and so on. So the question is how to connect those small pieces of work with the firepower of a GM, let's say, or Boeing, or what have you.
Or a Siemens or a Dassault or something like that. Well, you know, So we do a fair amount of pretty sophisticated physical modeling as well, you know, both for our product and our manufacturing processes. What we can't do is figure out how to perform those at the same, while we're doing a digital mock-up, if you will. You know what I mean? And but anyhow, you're right. What we're trying to do is incorporate some fancy nonlinear materials and nonlinear behavior into these kinds of design systems.
I think that's about all we have time for, so thank you again,
Okay.
Bob.